Welcome back. In this video, we'll be discussing the pH system. And the basis of the pH system is what's called the autoprotolysis of water. That's a $10 word, but what it means is that an equilibrium is established in water in which a proton, that's the proton is transferred from one water to another water and creates hydronium ion and hydroxide ion. Only a small fraction, 1 in 10 million waters do this, but it is an equilibrium that's maintained, and as such we can always figure out the H3O plus concentration if we know the OH minus concentration and vice versa. The language I'm using I need to break out for you. So let's take a moment and break out these words. First of all, I ask you to familiarize yourself with the name of H3O plus, it's hydronium ion, and you've known the name of hydroxide ion. Hydronium ion is how H pluses exist in an aqueous or water environment. We call H plus a proton. Why do we call it a proton? If you look at the hydrogen atom, what is in a nucleus? You say 1 proton. Are there any neutrons in the hydrogen nucleus? Well, 99.999% of hydrogens do not have a neutron because the average mass of hydrogen is 1. If they had a neutron in here, their mass would be 2. A small percentage of hydrogens have a neutron. That's called deuterium. It's radioactive. And an even smaller percentage have 2 neutrons, and that's called tritium. But most hydrogens have just a proton in the nucleus and just an electron surrounding. When they lose that electron to form H+, what do we have left? Just the proton. So the common lingo is to call it a proton. Well, it loves hanging out with those electrons on water. It's electrostatically attracted. So all protons in an aqueous environment really exist as hydronium ion, but we can use them interchangeably. It's understood. H pluses, H3O pluses, same thing. Okay? Alright, so let's go into the equilibrium that exists. H2O hitting H2O, transferring a proton, making H3O plus, OH minus. We see the double arrow here. The double arrow is a new thing to us. It's an equilibrium. What is constant is the H3O plus concentration. Here's a new deal. These brackets mean molarity. The molarity of H3O plus times the molarity of OH minus, it's a constant number, 10 to the minus 14. This is at a certain temperature, 25 degrees room temperature. This is such an important constant, it's called the ion product constant for water. So the gist of this is, if I know one, I know the other, because they multiply together to be 10 to the minus 14. Here it's stated in words, water is amphoteric, it acts as both an acid and a base. In pure water, water can self-ionize, transfer a proton from one to the other. You would have just as many H3O pluses as OH minuses, so they equal each other, and that is 10 to the minus 7th. The ion product constant for water is the H3O plus times the OH minus, which is 10 to the minus 14th. This is the basis for the pH system being on a scale of 1 to 14. The 14 is this exponent. It's also the basis for pH 7 being neutral. That's when the H3O plus is 10 to the minus 7. We have an equilibrium sustained. If I add more acid, I would be increasing the H3O plus. Well, to maintain equilibrium, this must go down. My concentration of OH minus must drop if I'm increasing my acid. Vice versa. Alternatively, if we add base, to the water, it must be, since this concentration times this concentration is always 10 to the minus 14, that the H3O plus must go down to compensate. If my H3O plus is 10 to the minus 5th, then it must be, my OH minus must be 10 to the minus 9th, and they multiply together to be 10 to the minus 14th. Likewise, if my H3O plus is 10 to the minus 11th, my mouse, I'm losing my mouse, 10 to the minus 11th, then my OH minus must be 10 to the minus 3rd. They move opposite each other. Another thing I want to look at is the powers of 10. We have not yet defined pH. pH is the log of the H plus concentration. So a log represents the power on the 10. If I have 10 to the minus 4th molar, big M, H3O plus, the power on the 10 is minus 4. pH is minus the log, so I make it positive. So 10 to the minus 4th is a pH of 4. If I say that means I've got one H3O plus ion in the water, if I then say it's 10 to the minus 3 molar, I'd have 10 times more H pluses, and it's shown graphically here. If I say I have 10 to the minus 2 molar H3O plus, I would have 100 times as many H pluses. Something to keep in mind, there's a 100-fold difference between pH 2 and pH 4 is the bottom line of that. We'll first use this table to learn how to do pH, pOH, and convert between hydrogen ion concentration and hydroxide ion concentration. And from there we'll move into word problems. I think you'll find that this framework helps you keep straight the moves that you need to do to convert. So we have some important relationships. They're all stated up here with equations. These first two columns sum to 14. The hydrogen ion concentration times the hydroxide ion concentration is 10 to the minus 14th. When I have provided an H plus concentration, I will log it to go this way. This will be the log direction. When I have the pH value, or the pOH, I will use the anti-log, which is 10 to the minus pH. Okay, so those are the basic moves, and so let's practice this. The pH of 2 means the pOH must be 12 because they sum to 14. If I know the pH, then I can find the hydrogen ion concentration because it's 10 to the minus pH. I can do whole numbers in my head. That is not a challenge, but what is a challenge is when it is not a 1 in the base. Then you must use your calculator. So what would this next line be? This one's one that you can do quickly in your head. Hopefully you put a 3 here, and you said, okay, 10 to the minus pH. Hydroxide is 10 to the minus pOH. Alright, so the next line is not as obvious. I'm given H plus. I need to log those complicated looking numbers. I know just from the power in the 10 it's going to be in the vicinity of a 9 when I do that. You go log, I'm going to write this out, I go log of 4.5 E minus 9 on my calculator, and when you do that you'll get a negative 8.35, but the pH function is negative log. We always have positive numbers over here, and I'll write 8.35 and you're like, well, that has 3 sig figs and you were only given 2 sig figs, but not with pH, not with log functions. The front number expresses the power in the 10. These are the sig figs, so this is 2 sig figs. If this is 8.35, then 14 minus this gives me my pOH, which is 5.65. And then my hydroxide ion will be 10 to the minus POH, but this is improper, and so I need to put that into my calculator, and when I do that, I'll go 10 caret negative 5.65, and I will return a proper scientific notation of 2.2 times 10 to the minus 6. Let's do one more and then you can complete the rest of this front side of this worksheet. I'm being given an OH minus concentration. What would you do from this point? Right, log it and put it in the POH box. You get 4.07. When this is 4.07, 14 minus that will give me my pH, which is 9.93. So my H plus will be 10 to the minus 9.93, which is improper. I put that into my calculator, 10 caret negative 9.93. I get 1.2 times 10 to the minus 10. Now, one final thing I would like you to get into the habit of doing is to check your work. I want you to get into the habit of looking at the power on the 10 and looking for consistency in the numbers. Okay, do you see how logs express the power on the 10, and there should be a lot of consistency between that number and that power on the 10. Here, they'll be off by a little bit because these bases aren't all ones, but check your work and you'll catch errors that way.